Dr. D. Sangeeta is currently a senior lecturer at the Department of Chemistry, Anna University, Chennai. She has completed her PhD in the field of polymer chemistry from the University of Madras in the year 2000 and has teaching and research experience of more than 10 years. Her research interests are in the following fields: fuel cells for clean energy, functional membranes for desalination, and polymers for biomedical applications. She has published more than 20 research articles in national and international journals and has more than 40 research articles in national and international proceedings. Presently, she is guiding 6 research scholars for their doctoral degree.
Welcome to UGC lecture series. Today in this lecture on the subject of polymer science for the part 7 or lecture 7 of the unit Characterization and Analysis of Polymers, we will be exclusively talking about the molecular weight, different types of molecular weights, its distribution and molecular weight distribution curve and the significances of all these. So, the contents are going to be the basic definition of molecular weight, different types of molecular weights which are otherwise called as average molecular weights of polymers, what the molecular weight distribution is all about in case of polymer molecules, and how do you determine such molecular weights. Molecular weight distribution. The most simplest and common molecular weight is called the number average molecular weight. Although there are different types of molecular weights, average molecular weights for polymers, the most simplest one is the number average molecular weight. Such a type of number average molecular weight of a polymer sample can be determined by N group analysis methods or colligative property based methods like boiling point, elevation, osmotic pressure, depression and freezing point, and so on. Such a type of molecular weight, which is called as number average molecular weight, has a particular specific method in which the calculation can be made if you know the number of molecules having the different molecular weights of the individual molecular chains in a particular sample. Other types of molecular weight that are available with respect to the polymers are also available, which are called as the weight average molecular weight represented by MW, Z average molecular weight MZ, and viscosity average molecular weight MV. These different types of molecular weights can also be determined by various methods. The methods which are suitable to determine molecular weight based on weight is the light scattering method. Sedimentation equilibrium method is more suitable to determine the Z average or the sedimentation average molecular weight, and the solution viscosity method is suitable to determine the viscosity average molecular weight. Hence, there are 4 types of molecular weights whose calculation or whose determination, how it can be done, is what we are going to see right now. The first type is the number average molecular weight Mn bar. Based on the methods of counting the number of molecules that are available in a given weight of polymer sample, if the calculation is done, then such a type of molecular weight you call it as number average molecular weight. The total weight of the polymer sample, let us say, is W. It is the sum of the weights of each molecular species that are present in the whole of the sample. Suppose, let me say, there are 10 different types of molecular weights and each type of molecular weight is available in different numbers. Then the total mass of the polymer sample that is available for the calculation is given by the molecular weight multiplied by the individual number of molecules that are available. If you are going to add up all the number of molecular chains available with its own molecular weight, that is supposed to be the total weight of the polymer. Hence, a very simple and a basic formula like this is used to determine the Mn bar or number average molecular weight. This is given by Mn bar is equal to W by the summation of the total number of molecules present in the sample, wherein W is equal to Mi Ni. The summation of the Mn Ni is nothing but M1 N1 plus M2 N2 plus M3 N3 plus ... till all the numbers accumulated in the series. For example, if I say M1, N1, N1 number of molecules are having M1 molecular weight. Similarly, M2 number of molecules possessing M2 molecular weight, and so on. All of them, if they are put together, you call it as the sigma MINI, which is nothing but the weight, the total weight of the polymer sample. If this is divided by the total numbers of molecules available, this directly gives you the average molecular weight of the polymer. So, the total weight W, which is calculated by taking all the number of molecules with their corresponding molecular weights divided by the total number of such molecules that are available in the sample, which directly gives you the number average molecular weight, and hence N refers to the number of molecules, M refers to the molecular weight. So, such a simple calculation can be done if you know the different types of monomers, the polymers with their corresponding molecular weights. The second type of average molecular weight is called the weight average molecular weight, represented by MW. The determination of molecular weight, if it is based on the size rather than the number of molecules, then this calculating method leads to the weight average molecular weight. Greater the mass, the greater the contribution of it to the measurement. That means, in general, greater the mass is going to be the case if there is a greater number or number of repeating units. If it is greater in a polymer chain, the mass is going to be more. So, hence this is directly reflected in the weight of the polymer sample. This weight average molecular weight is given by a simple formula like this, where MW bar is given by summation of Wi Mi divided by the total weight, which is again equal to sigma Ni Mi square, where N represents the number of molecules, M represents the molecular weight of the corresponding polymer molecules, and W is the weight fraction. So, the difference between the number average and the weight average is now felt. In the previous case, it was only Ni Mi, which is a total weight divided by the total number. Now, this is Wi Mi, which is nothing but Ni Mi into another Mi, which is nothing but Ni Mi square. So, this can be expanded as N1 M1 square plus N2 M2 square plus N3 M3 square, and so on, which is nothing but the number of molecules N1 having the molecular weight M2 M1, its square, and this is added with all the series. This is divided by a value of Ni Mi sigma value. This directly gives you the weight average molecular weight, where W represents the weight fraction, M represents the molecular weight, and N represents the number of molecules whose corresponding molecular weights are given by the same number with M. There are two more molecular weights. One such molecular weight is called the Z average molecular weight or sedimentation average molecular weight. Some molecular weight determination methods includes the sedimentation equilibrium. They yield a molecular weight which is called Z average molecular weight. The formula is simply extended from the number average to weight average to this Z average by including one more Mi factor here. So, this formula becomes sigma Ni Mi cube divided by sigma Ni Mi square. So, in the case of number average, it is sigma Ni Mi by sigma Ni. In the case of weight average, it was sigma Ni Mi square by sigma Ni Mi, and in this case it is sigma Ni Mi cube divided by sigma Ni Mi square. Now, this method is very useful to determine the Z average molecular weight. Now, let us try to understand these calculations by making use of a simple example. Take the case of a polymer sample. Let us assume that it consists of 9 molecules of molecular weight 30,000 and 5 molecules of molecular weight 50,000. This may not be a true case at all, because it may contain several number of molecules having several types of molecular weights individually that are present. For the sake of simplicity, we will consider the sample containing only 9 molecules. If it is containing 9 molecules, it is not a polymer, but for the sake of simplicity, we are taking 9 molecules wherein they contain 30,000 molecular weight and 5 molecules containing 50,000 molecular weight. Now, by making use of the basic formula Mn bar, number average molecular weight is given by sigma NiMi, which is nothing but 9 into 30,000, where 9 is the N1 and this is your M1, plus N2 M2, where 5 is the number of molecules containing 50,000 molecular weight, whole divided by total number of molecules, which is nothing but 9 plus 5. So directly this gives an answer of 37,000. So the 37,000 is the number average molecular weight of this polymer sample. So this could be extended to any numbers if you know the different numbers of molecules having different molecular weights in a particular polymer sample. Similarly, let us do the same way of illustration for calculating the weight average molecular weight. In the case of an example where the polymer sample containing the same 9 molecular weight 30,000 and 5 molecules of molecular weight 50,000, MW bar is given by NiMi square by NiMi. So it becomes 9 into 30,000 square plus 5 into 50,000 square, which is nothing but the number of molecules M1, which is 9, is multiplied by its own molecular weight square, which is nothing but M1 square. This is N2 M2 square, and this can be extended if you have several numbers. The whole thing should be divided by 9 into 30,000, which is NiMi sigma, that is N1 M1 plus N2 M2 plus dot dot. This directly give you the value of 40,000. Now note down, for the same polymer sample, when we tried to calculate the number average molecular weight, it was 37,000 and it is 40,000 now, and hence the weight average molecular weight is higher than the number average molecular weight. Both of them are two different types of representation, that's it. The third type of molecular weight for its calculation is at average molecular weight. Let us take the same example of 9 molecules with 30,000 molecular weight and 5 molecules with 50,000 molecular weight. The formula is once again changed here. It becomes NiMi cube, that is N1 M1 cube plus N2 M2 cube and so on, whole divided by N1 M1 square plus N2 M2 square plus dot dot. This becomes 42,136. This is now again a little more than what we have seen in the previous case. So we can understand that in a dispersed polymer sample whose molecular weight is not uniform, that means a sample containing different molecular weights for the different number of polymer chains that are available in the polymer sample, you could have different average molecular weights, namely a different number average, a different weight average and a different Z average and so on. Now let us talk about the distribution of the molecular weight with the help of a molecular weight distribution curve, which is very popular. Coming to the molecular weight distribution, narrower the molecular weight range. That means if I have a sample wherein there are lakhs of polymer molecules, the same polymer structure, polymer molecules available in the sample, but each one of the molecular chain has or possesses different molecular weights, and this different molecular weight is in the same narrower region. That is, when we say there is a closeness between the values of MW bar and MN bar, that means the number average and the weight average molecular weights are very close to each other only when the range of distribution of the molecular weight are narrower, or the molecular weight of the different polymer chains available in the same polymer sample are very close to each other, then you can expect the MW average molecular weight and the MN average molecular weight to be as close as possible to each other. Hence, the ratio MW by MN may be used as an indication for the molecular weight range in a given polymer sample. If it is very broad, if they are more different in values, then you can say that the distribution of the molecular weight is very high. If it is narrower or the distribution is very low, then you can say the ratio attains a value very close to 1, or the MW and MN values come very close to each other. Now, this ratio MW by MN, this particular ratio is also called as polydispersity index, shortly PDI. This ratio basically indicates the molecular weight distribution of the polymer chains available in the polymer molecules. Any system having a range of molecular weights is said to be polydispersed. That means, if a polymer sample has got variety or different molecular weights then the system you call it as a polydisperse. If all the polymer chains in a particular poly sample is highly uniform and contains the same molecular weight, then it becomes a narrower range and the molecules are said to be dispersed, monodispersed in nature. Generally, it does not occur unless you make use of certain technologies or certain Ziegler-Natta polymerization or coordination polymerization technique to make highly uniform and highly isotactic polymers, which could be obtained only by those methods. You can achieve very close to 1 value, but it cannot be equal to 1. So, you always have a polydispersed sample and you can never produce a monodispersed sample, but very close to monodispersion can be made by artificial methods. Now, what is the significance of this value or the ratio polydispersity index? This is basically by calculation or by measurement is equal to MW by Mn, that is weight average molecular weight divided by number average molecular weight. When this PDA value is approximately equal to 1, it cannot become equal to 1, but when it is becoming very close to the value of 1, the distribution is said to be narrow. But when the value is far away from 1 or greater than 1, you can say the polymer molecular weight distribution is highly broader. If it is 1, then the sample may be called as a monodispersed sample. The condition you call it as a monodispersity. PDA can never be less than 1, because according to the formula, the weight average molecular weight is always greater than the number average molecular weight. Now, this kind of molecular weight distribution can be put in the form of a curve called molecular weight distribution curve. Now, you could see that the distribution plots may take any of these types. For example, the first curve indicates a more narrower sample. That means the dispersity is less here. It is approaching monodispersity, but it is not a single line. You do not have a single line at all. If it approaches a single line, then you call it as a monodispersed sample, but it is a narrower range. If you take this case, x axis indicates the Ni or the number of polymer molecules in a sample, and Mi indicates the molecular weight of the corresponding number of polymer molecules in the polymer sample. If you try to plot this curve, this is a broader curve. There are possible complex curves which could be like this also. So, the curve gives a fair idea about the dispersion or the dispersity nature of the polymer molecules available in the sample. Same type of polymers may be having different distribution and hence may behave differently. So, what is the use of knowing this distribution curve? When you try to analyze the curves, it gives a fair idea about the properties of the polymers. Why do they behave differently? When they have different types of curves, they behave differently, their properties are different from each other, although the same polymer structure or the chemical structure is the same. You might have low and high polydispersity materials. This is a low polydispersity sample. Second curve represents a high dispersity sample. The third curve represents a complex distribution. That means you have a broader distribution, but at the same time a small number of molecules have greater molecular weight. This region is higher. So, you may have more and more types of complexity also that could be present in a given sample. If you try to draw the curve and then try to analyze, you can get a fair idea about the performance or the properties or the behavior of such materials, how they will be doing in the service life. Now, what is the effect of polydispersity on the polymer properties? If you have a very narrow molecular weight curve, for example, A is supposed to be a narrow curve, the strength and toughness of such polymer samples increases very nicely. That is because of the reason that almost all the polymer chains are uniform or very close to each other. There is no much variation in the molecular weight. Similarly, when you have a broad molecular weight distribution curve, which is indicated by the curve B over here, when compared to A, B is supposed to be more broader. These polymers are very difficult to be processed. For the processing of the polymer materials, to make them converted into a suitable product, you make them to undergo the processing. During the processing, if all the molecules of the polymer molecules are uniform or having the same range of molecular weight, it is easier and convenient for the processing to take place. Whereas, when the molecules have different distributions, different molecular weight ranges, the process becomes difficult and complex. There is an analysis called GPC analysis, gel permeation chromatographic method. It basically provides the key information to predict about the sample, their processing characteristics, the processability of the sample, and the material properties of a polymer. This GPC analysis, which we will be seeing in the next class, gives a fair idea about the polydispersity index, and it gives the molecular weight distribution curve of the polymer sample under test. So, from which you can predict how good or how complex the processing of such polymers are going to be, and what kind of properties are going to be reflected from such polymers. The other type of molecular weight, which is otherwise called as a viscosity average molecular weight, is basically based on the viscosity of the polymer solution that are prepared as a solution from the polymer samples. Basically, viscosity is greater for larger polymer molecules than the smaller ones. MV is much closer to MW than MN, and this type of molecular weight is determined based on a method called viscometry. Basically, the polymer is prepared in different concentrations, different viscosities of solutions are available, and the flow time required for the flow of such solutions, flow of such different concentrated solution or different viscous solutions are made used for the calculation purpose, and such molecular weight whose calculation is based on the viscosity of the polymer solution is called the viscosity average molecular weight. And approximately they can be given by a formula like this. MV bar, similar to the other types of molecular weights, MV bar is given by sigma Ni Mi to the power a plus 1 divided by sigma Ni Mi whole to the power 1 by a, where W represents a weight fraction, N represents the number of molecules, M represents the molecular weight, and a factor called A, a parameter A is introduced, which is a constant. When the value of A is equal to 1, we say that viscosity average molecular weight is equal to weight average molecular weight, because the formula comes down to the same formula which we have used for the weight average molecular weight, because this becomes 1 and therefore sigma Ni Mi square divided by sigma Ni Mi whole to the power 1 by 1 will become 1. So, this is the same formula which we used for the weight average molecular weight. But in general, A's value is between 0.5 and 0.1, it does not reach 1. A is a constant which is a measure of the hydrodynamic volume of the polymer when it is present in the solution form. It varies with polymer, it varies with the solvent used for the preparation of the polymer solution, it also depends on the temperature of analysis. Now, coming to the determination, having seen the 4 different types of molecular weights, namely number average, weight average, Z average, and an introduction to the viscosity average, and also we have seen what a molecular weight distribution curve is. Now, how do we determine practically, how do we analyze and determine the molecular weight of a particular sample? There are basically 2 important methods which we will be discussing in our classes. Although there are light scattering, osmotic methods, colligative methods and so on, we will be confining to gel permeation chromatography and viscometry methods. Now, this gel permeation chromatography, which is otherwise called as GPC method, is a most convenient and a comfortable laboratory based method which uses a sophisticated instrument called GPC. Their calculation is based on the fractionation of polymers. What do we mean by fractionation of polymers is separating the polymer sample, which is polydispersed in nature, into several fractions due to the sieving action. This is basically depending on the size of the polymers. Basically, when the polymer chain is bigger, the size is going to be bigger and the molecular weight of such polymer is also higher. So, this separation or fractionation of a polymer sample into different molecular weight ranges, smaller ranges, and they are fractionated or isolated depending on the molecular weights, and this, if it could be done by making use of a chromatographic column, this method gives a way to determine the number average and weight average and also the PDI factor along with the molecular weight distribution curve. Hence, this basic method, which is based on the size of the molecules, size of the polymer molecules. If the size of the polymer molecule is more, it takes a lesser time to elute from the chromatographic column and then comes out. Whereas a smaller molecular weights has a capacity to be retimed due to several actions which are going to take place throughout the chromatographic column. They come lately, or the retention time for the larger molecules are lesser, and for the smaller molecules the retention time is higher. So, based on this size exclusion principle, the molecular weight of the sample is determined. Hence, the method is also called as size exclusion chromatography, or SEC. The method basically involves two phases. One remains stationary in the column, the other one is the mobile phase, which is the basic polymer solution which is carried through the stationary phase, and the separation or the fractionation occurs depending on the size of the molecule, which in turn depends on the molecular weight of the polymer chains. So, this is one particular method. The actual procedure, principle and the formulae and the calculation part will be done in the subsequent class. The other important method, which is very commonly used, again a laboratory method which does not involve any sophisticated instrument to be used, is the viscometry. This viscometry method basically gives the viscosity average molecular weight very quickly in a laboratory. This method uses a viscometer, which is a glass apparatus which is used to measure the flow time. Now, the basic principle behind this method is the concentration of the polymer solution, or the polymer solution is prepared in different concentrations. When the concentration is higher, the viscosity is higher. When the molecular weight of the polymer is higher, the viscosity is higher, depending on the fact that the viscosity of the different concentrated solutions of the same polymer for the different concentrations, and based on the different concentration and different viscosity, the time taken for the flow of such different concentrated solutions are going to be different, or the flow time required for the different concentrated solutions are measured in the method. And when you are going to measure this, you can observe that more viscous solutions, more concentrated solutions take more time to flow a particular region, whereas the lesser concentrated solution or the lower concentrated solution, they take less time to cross a particular region. So, depending on this, depending on the viscosity, depending on the time to flow for the polymer solutions, the calculation is done. So, here in this case, the method also uses a very popular equation called Markov-Wink's equation, which tells you that the intrinsic viscosity is given by K m bar A, where m is the viscosity average molecular weight and K and A are constants which depends on a particular polymer in a particular solvent at a particular temperature, and these values are constantly available which can be directly used, and intrinsic viscosity can be determined by the experimental procedures and m can be directly calculated from the equation. The details about these plot and calculation will be dealt in detail in the next class. Now, today we have seen the molecular weight of the polymers, particularly average molecular weights, the different types of average molecular weights, how are they calculated. We have also seen the molecular weight distribution curve and its use. We have defined the polydispersity index and the significance and effect of PDI on the polymer properties have been seen today. Here are few questions. What are the different types of polymer molecular weight? How do you calculate Mn, Mw, Mz and Mv? What is a molecular weight distribution curve? What information are derived from a MWD curve? Define PDI. What is its significance? Brief on the effect of polydispersity on the properties of polymers. Thank you.